Hello, KD. My name is Abhijit Bose, and I lead the Center for Machine Learning at Capital One. As I have been attending the sessions over the past couple of days, I can't help but think that this is truly the golden age of machine learning. The demand for ML talent, including machine learning engineers and data scientists, is just unprecedented. For instance, if you read LinkedIn's 2020 Emerging Jobs Report, you will find out that AI roles had an annual growth of 74%. That's quite a jump in demand. While many companies like Capital One have been leveraging AI and ML across the organization for some time, we have seen the COVID-19 pandemic accelerate technology transformations and adoption of machine learning for many companies like ours. And the demand for talent is not just for those who have PhDs and have been in this space for many years. Companies are looking for talent at all levels. If you have a STEM background and enjoy software engineering, you can be a machine learning engineer or a data scientist. Do not let anyone else convince you otherwise. I will also say that the golden age of machine learning goes beyond the demand for talent. Machine learning needs data, and the more data you have, the more opportunities to build robust ML models and systems. And also, with the advent of deep learning and deep neural networks, a lot of the problems in the past that people thought were too hard, like recognizing objects in images or transcribing speech or voice recognition, are now possible. So with this combination of the availability of data and huge computing resources, there are a lot of opportunities to use machine learning in many companies and industries right now. At Capital One, machine learning, AI, and real-time data have become central to how we build our products and services for our customers, and also just how we run our company. Data is critical to our organization. With the type of cloud platforms we have today, we have the ability to manage data in real time. We have the ability to apply sophisticated machine learning models to help us with insights that ultimately deliver better products and services to our customers. We are applying AI and ML to solve lots of real world problems at scale that improve people's lives, such as fighting fraud, creating technologies that ease financial stress, digital assistants that understand you, and applying ML to extend credit to those without a credit history. We are also applying it to our internal use cases, like determining whether some piece of code is ready to be deployed to production, detecting anomalies in various systems, and just how we optimize our cloud infrastructure. We are developing platforms to build and train all of our machine learning models on the cloud natively. That involves developing fine-grained access control, needing to scale up and down resources, distributed computing, the proper checks and balances once you have built your models, ensuring explainability, and lots of infrastructure problems that we have to solve along the way. As you can see, it truly is a golden age for machine learning, and so many great opportunities for machine learning engineers, data scientists, and just about everybody involved in ML and AI today. I hope you enjoy the final keynote of the conference, and all the best with your career in data science and machine learning.
Hi. Thank you so much for this opportunity to present our work. I want to start by saying that I regret not being able to see everybody in person at a physical conference. Of course, given the circumstances, this is the right thing to do. And we will have a Q&A session after, but normally at a physical conference, I might stick around a little bit longer and answer more questions and maybe go to dinner with some people, and now we can't do all that. So I want to encourage anybody, if you have any questions or comments, please feel free to reach out by email or find me on social media, or maybe one day again, find me at a physical conference and we can talk there. So this is joint work with a lot of wonderful people. I'm going to start by pointing out Hanrui Zhang. my amazing PhD student, and this is mostly his work. So please keep your eye out in case you're looking to hire people in the near future. He will be on the job market someday soon. And you'll see him appear throughout almost the entire talk. Except maybe a little bit closer to the beginning of the talk, I'll talk a little bit about Andrew Kephardt's work, who was a PhD student here as well at Duke, but is now at Instacart. And then there is Yu Cheng, who was a postdoc here at Duke and is now at the University of Illinois, Chicago. And so he was involved in some of the theoretical work. And then the last three people were involved in the relatively more experimental work that I'm going to talk about at the end. So that's Anilesh Krishnaswamy, who is a postdoc here now at Duke and is about to join Google. Haoming Lee, who was a master's student here at Duke and is now a PhD student at the University of Southern California. You might remember him as one of the workflow chairs of AAAI 2020. So he did a lot of wonderful work for that. So thanks to him for that as well. And David Ryan is an undergraduate here at Duke. And I thought for a while about what to present. So another talk I might have given is I have another talk on reconceiving how we think about agents in artificial intelligence. That is a little bit more of a philosophical talk. If you're interested in that, you can find it on YouTube or ask me questions about it. But today I really wanted to focus on what I think is more interesting to this audience. And so what is this talk about? This talk is going to be about settings where we can't quite trust the data. But we're going to not be able to trust the data for a specific reason in this talk. So I'm not going to be concerned with settings where there's just noise in the data. Maybe there's messy data entry or something like that. I'm going to be concerned about settings where it's actually due to strategic aspects that we can't trust the data. Specifically, agents, maybe people submit data, but they submit it in a maybe intentionally corrupted way to get a better outcome for themselves. And this leads us into techniques from game theory and mechanism design. I'm not going to assume any background in game theory or mechanism design. So maybe if you don't know anything about that yet, you'll come away from this talk knowing a little bit about that as well. So much of the talk is going to be fairly theoretical to try to get a good sense of what we're really trying to do. But then towards the end, as I already said, there are going to be some experiments with real data as well. So that is our setup. Let's get started. And so the context is that AI or algorithms are making a lot of decisions about us as human beings, and we care a lot about the outcome of those decisions. For example, algorithms might determine whether you get a loan. This, of course, is true broadly, right? There's usually specific policies or algorithms that determine whether you get a loan. For the purpose of this talk, probably the best example is that China's tech companies now offer many of their users loans or credit based on all kinds of data that they have about their users, right? So very much a machine learning kind of problem, and so that motivates very well the kinds of things I'm going to talk about today. Another example is where you get a job. In particular, AI is increasingly used for scanning and screening resumes that are submitted in job applications. So those are my two main examples that I think fit the best. There are two more that I think are reasonable. So another example, also a consequential one, is will you get a date? Increasingly in online dating apps, artificial intelligence is also used to match people together. And so you might care quite a bit about who you're matched with. Now, this is not going to be one of my main examples. And one of the reasons is that I don't really know too much about dating apps. I exited the dating market before those really became popular. So there's a picture of a younger me with my wife. So as you can see, I look a little bit older. She still looks the same somehow. But so I'm not going to focus too much on that, but that would be a reasonable example as well. And then finally, there are applications of AI in the criminal justice system, such as will you get out on bail? These are more controversial applications of AI, obviously, and I don't really want to consider this an application of this talk. In some ways, that fits. In other ways, these are very serious issues. If you take away somebody's freedom, we have to be very careful about that and treat that very seriously. So for the most part, I don't want to consider this an application of the techniques in this talk. But the first two, I think, are the best to keep in mind during this talk. Let's talk a little bit more about China's tech giants and their use of their data to offer their users loans. And so just from a little bit of searching the web, I was interested in particular in what kind of features do they take into account? What do they want to know about their users to determine whether they get a loan or not? And so you can find some evidence here and there. So records from payment systems that they use, that would make a lot of sense, right? That you would want to take that into account in offering somebody a loan. But also things like, did they return a shared power bank on time? And then it also says you can give even more information. You can give your record of house purchases, or maybe your LinkedIn profile, and that might help you as well. And then there's some other evidence that maybe, whether you use similar apps and websites or receive certain calls. I really don't know exactly what they use. Now, I don't want to pretend to be an expert on that or what exactly they're doing. But certainly a lot of this seems to suggest that they take all kinds of data into account. Here is another graphic I found that seems to suggest that here, for example, Tencent also looks at records of calls and texts to confirm personal relations and guard against organized crime. Okay, so the main point is they take all this data about people into account to decide whether to offer them something like a loan. Good. Now, these are potentially high stakes decisions for the users involved. And so it shouldn't be surprising that people think a lot about how to present themselves in such a way that they will in fact get a loan. Right. So here I found an article on how do you get your loan approved. This is not for the Chinese tech giants. This is, I think, more US focused. And it gives a lot of advice. And some of that really indicates what kind of features are being used to determine who gets a loan. For example, it points out here that one of the features that's often used is debt to income ratio. And so you might want that to look good. Now, there are multiple ways in which you can make it look good. One way is that maybe you get a second job and you work really hard and you pay off all your debts, right? And that in some sense really fundamentally changes who you are from the perspective of getting a loan, right? You will in fact have an easier time paying back future loans if you're not burdened by additional loans. But there are also ways in which you might just simply present yourself a little bit differently in a way that isn't really consequential. Maybe you rebalance your portfolio a little bit in a way that doesn't really make you better at paying future loans, but just changes the presentation. That second kind of scenario is what I'm going to be most interested in this talk. And then there are some other features, don't ask for too much, and so on. Similarly, resumes. What should you put on a resume? And this one here for now is not so much about AI scanning resumes, but just generally. So this article says, well, you might want to customize your resume to the job you're applying to. So maybe you want to remove irrelevant experience, but then on the other hand, if that just leaves a big gap in your resume, that's awkward too. So maybe you kind of want to represent it in such a way that it's more connected with the job. Is that legitimate? Is that just representing, or is that kind of lying? I don't know what they have in mind here. But so we'll come back to that. But certainly this idea that you might be lying comes up as well. And here it cites this study that says that 78% of applicants admit to lying on their resumes, and 66% of hiring managers don't actually care. I tried to find the study. If you click through there's a lot of articles that cite this study, but I can't find the actual study. So maybe the real message here is that 78% of such studies cannot be found anywhere, and 66% of reporters don't really care and cite it anyway. So don't take this study very seriously. But at least there's this awareness that some people might be kind of lying on their resumes. And it also points out that, well, you might actually get caught on the lie. You probably don't want to just lie arbitrarily. Okay. And of course, in no way am I going to endorse lying on your resume here in this talk. But just what are the things that we need to keep in mind? So here is an article that's more specifically about AI reviewing your resume. So what should you do if you want AI not to reject your resume? And it gives various advice. Don't use titles that are very unique to a particular company, because then the system doesn't have anything. It can't do anything with that. Also, some people are storytellers, but our natural language processing is still limited. So you want to focus on facts such as I led a team of 20 people and so on. Right? And this all makes a lot of sense, right? Because this does not seem to be lying in any way. This is just kind of presenting things in a way that makes more sense for the audience. In this case, an algorithm is the audience. And then there's this advice that maybe if you have a skill that is very relevant, but it's only in your resume once, just try to repeat it many times. Okay. So that's maybe, I'm not quite sure how honest that would be. Maybe depends on the situation. One more example is, this is not one of our original examples. This is actually pointing out that companies also adapt their speech to the fact that algorithms are scanning what they're producing, right? So if you look at forecasts and regulatory filings that these companies do, they are aware of the fact that algorithms are analyzing what they're saying and trading based on that. So a substantial amount of buying and selling of shares is done by algorithms that process information with machine learning and natural language processing. And it also points out that executives are aware of this and adapt their speech patterns accordingly. Okay, so what do we take away from all of this? So first of all, some actions that you can take really might change who you are from the perspective of the classification that's being done. That was this example of working really hard to pay off your loans. And so that really fundamentally makes you a different kind of borrower. That's not what I'm going to talk about today. Today, I want to talk about not really fundamentally changing your situation, but just presenting the information in a different way. And we've seen some amount of presenting the information might be desirable, right? This might be, for example, that you want to speak to your audience, and so you want to talk in a way that an algorithm can actually understand. But we've also seen there might be incentives to lie. And on the other hand, you might not be able to get away with everything. Some lies would, in fact, be caught. Okay, so those are the kind of high-level points I want to take away from all of this. That will set us up for what we're going to do later. So let's get a little bit more precise. We're going to think about classifying strategic agents. Okay, let's think again about the example of a loan. So here we have an example. So here we have an example of a person that is $2,000 in debt. That's negative $2,000 in their account. And we also know that A and B are the friends of this person, right? Those are the features of this person. And maybe it turned out to be a bad idea to lend to this person. And so from data like that, we learn a classifier. We have training data that produces a classifier. And maybe the classifier that we come up with is, if B is a friend, don't lend to that person. Right? Maybe that's the correlation that it picks up on. And usually the typical machine learning story sort of ends there, at least as far as coming up with the classifier is concerned. Then, of course, we have to evaluate it and so on. But here, I want to point out that, well, once you have the classifier, that also affects what data people submit, right? Because it might be quite easy, if you know that this is the classifier, to just temporarily drop B as a friend and say, well, sorry, I'm going to unfriend you for a while because I want to get this loan. And so the data starts to look like this, where B is no longer the person's friend. Okay. And so really, we would like the classifier then also to adapt to this behavior. Right. So maybe we adopt the classifier, and now the classifier is that we don't want to lend if the debt exceeds $1,000. And maybe now we've reached the stable point. So maybe you can see some game theoretic reasoning coming up here already if you're a little bit familiar with that. But that's how we're going to be thinking about this. And actually, more specifically, we're going to be thinking from the perspective of mechanism design. So what is mechanism design? Mechanism design is about making systems that work well, even when agents are acting strategically. So what we're going to be thinking about is we commit to a classifier, and we do so in a way that we know we're going to get good results, even if agents adapt to that classifier strategically. That's the setup. Okay. And this isn't purely an adversarial setting. It's not zero sum. Some things both the entity classifying and the people involved might appreciate, and other things not so much. So before we get more into the technical details, I want to just briefly address, like, why should we even get involved in this? Is this something we want to get involved in? One concern that you might have with getting involved in this is that many of these processes end up being biased or biased in a bad way, or otherwise awful. For example, there's this sort of very extreme example where an algorithm was audited, and it seemed to mostly pick up on two factors: whether the person's name was Jarrett and whether they played high school lacrosse. Right? So there's a concern that it's very biased towards wealthy white males. So that's something to genuinely be concerned about. That's something I care about as well. Now, I think, if anything, that's a reason to get involved in this and make sure that these things actually make sense. This in particular is probably a pretty extreme example, and I can't imagine this classifier being very good, but certainly those kind of phenomena do come up in practice, and we should be cognizant of that and make sure that things actually work the way we want them to work. Good. Another intuition you might have is, well, I really want a human to be in the loop on these things. And that's something we hear a lot in the AI community these days. In some contexts, it maybe makes a lot of sense. If you think about autonomous weapon systems, or maybe at least offensive autonomous weapon systems, you want to have a human being in the loop. Maybe if you're talking instead about bail decisions, maybe you want to have a human being in the loop. At least you want some interpretability of what is going on. Now, human beings might also be biased in bad ways, so it's not totally clear what you want. But the really motivating examples here, such as getting a loan, getting a job, I don't think there's much sense in getting a human in the loop. If you force a human to be in the loop, it's probably going to look like this guy over here, who is formally in the loop, but just every single time approving what the algorithm is doing by pressing this big button. Another intuition you might have is something like, you want to give an underdog a chance, right? You might worry that really designing these systems to be totally watertight doesn't leave any option for somebody. Maybe there's somebody from a disadvantaged background that really has difficulty getting a loan, and so needs to change a couple of things to finally get that loan and work their way up and become a successful person. That kind of sounds like a nice movie that I would like to see, but reality is often the opposite. Often it's the wealthy and well-connected people that know much better how to manipulate the system. In mechanism design, a common example of this is placing students in schools. And it used to be that in various places, they used mechanisms for this that were manipulable, that the preferences over schools that you wanted to give were not your true preferences. You could do better by manipulating your preferences to get a better assignment. And when those kind of mechanisms were deployed, it tended to be the kids of wealthier parents that took advantage of that because they understood what was going on, and the less advantaged children did not benefit. And so that's a reason to go to what are known as strategy proof or incentive compatible mechanisms, which are mechanisms in which there's no benefit to lying. This also comes up a little bit closer to home in scientific conferences, in computer science in particular. As you may or may not know, there are some groups of people that try to manipulate the conference review system, for example, by forming coalitions to try to review each other's papers in ways that are not good. And this is something I've been working to try to address with all the wonderful people down here. Again, you see Han Rui, also Stephen and Ryan, students at CMU, and Nihar and Faye are faculty at CMU. And there too, just to tie this back, it's usually not people from a low-income country that are like the only AI researcher in their country that are trying to do this kind of manipulation. You have to be somewhat well connected in a community that's doing a lot of AI research to be able to even try to pull something like this. And so we're working hard on making that as impossible as possible. And there's a very personal motivation in this as well, since I was AAAI 2020 program chair, and so we saw some of this behavior. Okay, and then a final intuition why you might be uncomfortable getting involved in these kind of applications is just this idea of AI outsmarting human beings by being so robust and manipulating is somehow scary. Now, I think there are reasons to be concerned about AI starting to outsmart human beings. I don't think that's a crazy concern, but you do want to think about it carefully. Many of our initial intuitions tend to be off. I can't think of a better example than this picture over here of robots doing something. If you think about this picture for a second, why would you ever design robots in this way? This makes no sense whatsoever. So our initial intuitions about this might be far off. Doesn't mean it's not important to think about. And in particular, also here, another response to this is that, well, maybe now this is very much about people submitting data to AI, but at some point, it might really become algorithms submitting information to algorithms. And so the algorithms are playing amongst each other. That's something I'm very interested in, and hopefully the topic of a future talk. But overall, I think this is something we should be thinking about. And so let's get a little bit more into the details. So we need some kind of model of this type of situation. And in particular, we're going to think about this idea of misreporting. And this is also a familiar idea in mechanism design. In mechanism design, usually the kind of application is that there's an item for sale and I have some valuation for that item. I value it at $100, but I say that I value it only at $90 because I think strategically that's good. Here in this context, we're going to think about your private information as an agent, as a human being that's participating in this kind of mechanism, also known as your type in mechanism design. Your type is going to be basically just your feature values, such as who are your friends and what is in your account. And we're going to be interested in this misreporting relationship. So here I draw an edge or an arrow from one type to another if the former type can pretend to be the latter type. Right. So here on the left, we have somebody with $0 in their account, and we're going to assume that they can also pretend to be somebody with $2,000 in their account because they could just take $2,000 out of their account for a little while. Or you might be able to drop one of your friends temporarily, right? So that's what the arrows indicate. But we also assume that the arrows don't go the other way. You can't pretend in this example that there's more money in your account than there really is, and you can't pretend that somebody is your friend that really isn't. Okay, so this kind of graph is going to be relevant to us. I want to give you a little bit of background on mechanism design as it's usually viewed. And so not so much in line with the kinds of application we're going to talk about here, but just to contrast it. And this often involves selling items through an auction or something like that. The example here on the slide is the first version of this talk that I gave was at CMU, well, remotely, but at CMU, which is in Pittsburgh. In Pittsburgh, there's an American football team called the Pittsburgh Steelers. So that's the example here. And so there might be, let's say there's 3 kinds of tickets that you might buy. Well, there's a great ticket where you're really right on the field. There's a decent ticket where you can still see the field, but it's not as good of a view. And of course, also you might just buy no seat at all. We're going to assume that there are also 3 types of people. Some people are uninterested. Some people are a fan. And some people are what I'll call a true Yinzer. That's like a real Pittsburgher that really loves the Steelers. Here are some examples of true Yinzers. Okay. And then each of those types is going to have a valuation for each of the outcomes. So the uninterested type, so you as a subscript here, doesn't value any of these outcomes, doesn't care about football. So anything that even any ticket that you give them is just as valuable as getting nothing, which is 0. But the fan values the great seat a little bit more than the decent seat, and a little bit more in turn than not getting any seat. And the Yinzer really values the great seat and also still values the decent seat quite a bit. And of course, still 0 for not getting any seat. Okay, that's the kind of setup. And then what we want to have is a mechanism. So the mechanism tells you, it says, well, you report what kind of person you are, and I'll give you an allocation and a payment based on that. So if you say you're uninterested, you get nothing, you pay nothing. If you say you're a fan, you get a decent seat and you pay 50. And if you say you're a Yinzer, you get a great seat and you pay 300. And in this context, you can misreport in any way you like. So the edges go all the different ways. Anybody can misreport to be anything. That's the typical kind of mechanism design setup. This particular mechanism here on the left with these valuations turns out to be incentive compatible or strategy proof. Again, that means that you never benefit from lying about what type you are. If you're a fan, it's in your best interest to say that you're a fan and get the decent seat and pay 50 for it. Okay, that's an important concept, so we're going to come back to that. Now, there are many variants of mechanism design. And so here's a little 2x2 to illustrate that. So the kind of application we just talked about is here in this bottom left. It's a traditional application where any type can misreport anything, but they have distinct preferences. And it's the distinct preferences that allow you to do anything at all. Because in that context, if all the types have the same preferences, there's not much you can do, because whatever report you give the best outcome to, they're all going to say that report. And so you can't separate anything. We're going to be interested here on things on the right. But again, the things on the left, that's especially this bottom left corner, that's where most of the action usually happens in mechanism design, including 3 Nobel Prizes. And for me, a lot of my former group members have worked and done amazing work in this. But today we're going to talk about this part on the right, which is labeled as partial verification. Partial verification means that not every type can misreport every other type. So like the first illustration that we saw, you can't pretend there's more money in your bank account than there really is. That's the kind of setting we're going to be interested in today. And in those cases, your type is really not so much about what preferences you have, but rather about what your features are and what you can pretend your features are. So that's still interesting, even in the case of identical preferences, right? If we're talking about getting a loan, presumably everybody wants to be offered a loan. It doesn't hurt you to be offered a loan. So the preferences are in that sense the same. What's different is the features. Okay, so a little bit more mechanism design theory. There's something known as the revelation principle. The revelation principle says that in this context where there's no limits to misreporting, any type can misreport any other type, it never hurts you to use an incentive compatible mechanism, right? So anything you can achieve when agents are strategic, you can also achieve it by having a mechanism where nobody ever has an incentive to lie. Here's a quick proof by picture. If you had some mechanism that wasn't incentive compatible, and so agents strategically took all kinds of actions in that, and you still got good outcomes, well, then what you could also do is you could replace those agents with programs that are similarly strategic and taking the same kind of strategic actions. And now for those programs to work, you still have to tell them what type you are, what you really value, okay? But then you would still get the same outcomes, right? That they're just doing the work for you. And now you could consider this bigger system that consists of the original mechanism plus the programs as your new mechanism. And now it's clear that you have every incentive to tell your true type because your program plays on your behalf. But this story relies on the idea that any type can report any other type. Okay, and that's been very essential to a lot of our work. Something we've worked on, that I've worked on since almost the beginning of my PhD is automated mechanism design, where we treat the problems, such as the problem that we just saw with the Steelers, as an optimization problem. So you get all that information from that slide as input, maybe also a probability distribution over what types there are in the population, some objective, like maybe we want to try to maximize the revenue or something like that. And as output, it produces a mechanism such as the one that we saw. And this, in that kind of context, turns out to be a linear programming problem. Here's the linear program. You throw it to a solver, and it tells you exactly what payments each type needs to make and what allocation of a seat they get. Okay. So that's by way of background. But key to this is the revelation principle that I just told you about. And it turns out this revelation principle, right? So this idea that it doesn't hurt you to focus just on truthful mechanisms. Truthful is the same thing as incentive compatible. That idea is no longer true. So for example, here's an example. Suppose that anybody can, so now we're talking about actually over-reporting your bank account. Suppose you can say, well, you know, I really want my bank account to look a little bit better as I'm trying to get a loan. So I'm going to go to my friend and ask for $1,000 to borrow from him or her temporarily. I'll put it in my account. I'll look better, and I'll pay back eventually. So I haven't really become any wealthier, but I just make my account look $1,000 better. But let's suppose that 1,000 is the limit. Okay, then the misreporting graph would look like this. If you're really $2,000 in debt, you can pretend to be $1,000 in debt. If you're really $1,000 in debt, you can pretend to be $0 in debt, but you can't jump all the way from 2,000 to 0. What does this have to do with the revelation principle? Suppose your goal was you really wanted to offer loans to people who are really, right? So before they go like get little loans from their friends, that are really only $1,000 or less in debt. Can you do it? There is a way to do it. And that is actually relying on this kind of behavior. You say, well, if you can show me that your bank account has $0 in it, so not in debt at all, then I'll give you a loan. And what's going to happen is that, of course, the people who really are $0 in debt, they're going to get a loan. But also the people who are $1,000 in debt, they're still going to be able to get a loan because they can briefly pretend to have only $0 in their bank account. But the $2,000 in debt person will not be able to do that. So it is possible to achieve this goal, but you can't do it truthfully, right? Truthfully would mean that I don't give any incentives to manipulate your bank account, But if I say people that are naturally $1,000 in debt, that I can see in their bank account they're $1,000 in debt, if I give those people a loan, then also the people who are $2,000 in debt are going to get a loan from me because they will be able to pretend to be only $1,000 in debt. Okay, so that's a failure of the revelation principle. Here you benefit from getting people to misreport. And this is really what makes this kind of optimization problem very hard. So I won't go into the details here, but you see a lot of NP complete results here. So most of these problems are NP hard, even if you already kind of know exactly what outcome you want each type to eventually get. Fortunately, under some assumptions, the revelation principle does hold. In particular, if you have transitivity in this graph, then it will in fact hold. So here, for example, if you want, so here in this example, you can only over-report your debt, but you can't quickly borrow some money from your friend. And in that world, if you, for example, your goal is to accept people who are at most $1,000 in debt, that's possible. It's just a truthful mechanism that says, well, if your bank account shows at most $1,000 in debt, I will accept you. That will do the trick, right? Because the $2,000 in debt people will not be able to get to that point. There might also be goals that you can't achieve, right? Let's say, for example, we're actually trying to help disadvantaged people, and our goal is actually to offer a loan to people who are at least $1,000 in debt, but not the people who are really $0 in debt. That it turns out you can't do at all, right? You can't do it truthfully because then the $0 people would pretend to be $1,000 in debt. But there's in fact no way to do it at all, because even if you said, oh, well, you have to be $2,000 in debt, the $0 people would still be able to make themselves look that way. So the revelation principle holds, and that will help us quite a bit. Okay, and so that goes back to old results in economics. In particular, this result here is due to Green and Lafont from long ago. And then we have this kind of encyclopedic paper of all the different variants of this with costly signaling, where maybe you can misreport, but it's expensive to make yourself look different. That you can find a lot of these types of results in. Okay, and now I want to talk a little bit about the kinds of results that we can get in this kind of context. So what kind of good questions can a computer scientist ask him or herself in this context? Well, here's one. One question is just optimization, right? So actually trying to figure out the optimal mechanism. And here's a nice result that you can, in some cases, reduce this to a minimum cut problem, which we know how to do efficiently. So here's a picture, again, one of these misreporting graphs. And now each type is also associated with a value. And that value is how valuable it is to us, the entity organizing the mechanism, to accept that node. Right? So there's a couple here that's 2. So we would value accepting those 2s. That would give us 2 units of value to ourselves. But there are also some with -3. So those we'd really like to not accept. If you look at this graph for a little while, you see the optimal thing to do here turns out to be we want to accept the top 2 nodes here on the right, that are those 2 2s. That gives us 4. Now that has the disadvantage that then we're also going to end up accepting this -3 on the top left. But overall, that's still a win. 4 minus 3 is still 1. But this one down here, we don't want to accept. This 2 down here, if we accepted that, we would get the other -3, and that would actually cost us more. So the optimal mechanism here is to accept the top 3 nodes. And here's how you turn that into a minimum cut problem. We take the same graph. Now we put capacities of infinity on all the original edges. And now we add S and T, so it's ST flow. And we connect S to all the negative nodes. And the weight that, the capacity that we put on the edges to those is the absolute value of their original value. And the ones with positive value, we connect to T. And then we solve the minimum cut problem. The minimum cut here turns out to be this one. And so you see the minimum cut actually separates the nodes you want to accept in the optimal solution from the ones you want to reject. And that makes intuitive sense. Because so you can see here there was a node we wanted to reject but didn't, and so that costs us 3. We're cutting through that edge. And on the bottom right, we see there's a node that we wanted to accept it, but we end up rejecting it, and so that costs us 2, and that's where the edge cuts. But importantly, the edge never cuts an edge. Sorry, we never cut an edge that goes from the reject to the accept side. because that wouldn't make sense, because then that node on the reject side would in fact be accepted because they could misreport. That's the very quick summary of that. And this actually works not just in an accept reject setting, but generally as long as types have the same utility function. So in this top right part of the table I showed you before, then this works. Okay, so that's a kind of computational result. Here's an illustration with more outcomes than just accept and reject. I'm not going to go over that. Another thing that you can study is generalization, right? So we have to actually base these mechanisms on data, right? We generally don't know the prior distribution, how many people are this type, how many people are that type. And so we have to think about generalization. And an interesting thing is that if you consider incentive compatible classifiers, like we just did, then in fact, this imposes a kind of regularization. So again, the Hanrui-Zhang's result, that you can see that you have the following kind of inequality. So what is all this saying? We're talking here about the loss that some classifier F experiences. Sub D means that it's on the true distribution. Now, the one here on the left has a little hat on it, if you look carefully. That means, so the loss with the hat on it is the loss that you experience when agents are, in fact, strategically misreporting. Okay. And without the hat, they're reporting truthfully. Now, in this case, that's going to be the same loss because it's incentive compatible. So in fact, nobody will be misreporting. Okay. And now the trick is to relate that to the loss that you would experience on your sample, right? You're going to see how well the sample generalizes. And so how far off are you? Well, it's a function of this VC term, which we say is the intrinsic dimension of the feature space and reporting structure. So that graph that we saw before. Okay, so it's a function of that, the structure of that graph. How does that work? Well, it works as follows. We say, well, for a pair x and x primed, there may or may not be a path from x to x primed. So if there's a path from x to x primed in the graph, we say x can reach x primed. And then we're going to look for the largest set of nodes in the graph such that they can't reach each other. Okay. And the intuition for that is that those can kind of vary independently. Formally, in graph theory terms, you take the transitive closure of the graph, and then this is what's known as the width of the graph, the resulting graph. And just to illustrate that, so here, suppose that this is our feature space. These are the feature values you might have, any number from 0 to infinity. And the misreporting structure is now that you can always report a lower number than you really have. So maybe the bank account example. You can always take some money out of your bank account temporarily. And so now this is, of course, a very rich space. There's all kinds of classifiers that you could have on this space, enormous number. But the VC dimension is very small, right? Every node can reach every other node. So the VC dimension is 1. And that corresponds to the fact also that there are relatively few incentive compatible classifiers. The only incentive compatible classifiers are the ones that say you get accepted if and only if you're above some threshold. Right, so that's a much smaller space of classifiers, and all of those, in fact, generalize well, illustrating the result I just showed you. And that means you can just do an ERM algorithm, empirical risk minimization, and we have an efficient algorithm for that I just showed you before. Okay, now finally, last thing I want to talk a little bit about this real experimental data that we have, well, mostly real, I'll tell you about it in a second. And here we're going to focus on the idea that you can drop some of your feature values, right? So in real data, often some feature values are missing, right? So instead of having all the feature values, you might miss. So here a star means that the feature value is missing. That might be because somebody forgot to enter it. But that also may induce strategic incentives, right? So maybe I'm applying for a job, but I think that somehow my hometown where I live is a negative signal for the job, maybe because it's very far away from the job. And so I just don't put it on my resume at all. So that now this feature is missing from me. But that's strategic in that case. It's missing for a strategic reason, right? And so here you see this, the graph for this strategic aspect that you can drop here any feature. And it might be that for me, like feature 3 really was missing, right? So I really had a star there. But on top of that, I decide to drop feature 2. And so I end up here on the bottom left with only feature X1 left. And that's the kind of setting we wanted to look at. And then we could actually do something with real data. Okay, so here is are some results in real data. So let me explain what this table is saying. This is a credit approval data set in Australia, Germany, Poland, and Taiwan. And so we're analyzing this data set. And we're analyzing it in two ways. So any classifier that we look at, we can analyze in two ways. We can look at it as, we can say, well, what if everybody is just reporting truthfully? How well do the classifiers perform then? Right, so that's the true column in each case. But we can also think about people reporting strategically. So responding to the classifier and how well does it do then? Okay, that's the setting. And so you see the different columns. Okay, so a little bit more about the data. In the data that we had, actually nothing was missing. Now, if the only reason that features might be missing is because people dropped them strategically, then it's actually very easy to get good performance, because you would just say, look, if I see any feature missing, I know that somebody is manipulating me, so I'm rejecting that application, right? That could just be my rule. If anything is missing, I don't accept that application. And so as a result, nobody would drop their data and everything would be fine. It only gets interesting when some data is also naturally missing for other reasons, like the person really doesn't have a home address or something like that. And so to simulate that, we randomly dropped 20%, that's the epsilon is 0.2 here, of the features in our data set. So those were naturally missing. But then strategically, when we're evaluating strategically, we're considering the possibility that somebody also might drop additional features in order to get a better classification, meaning getting accepted. Now, what are the classifiers that we looked at? So everything you see here is based on logistic regression, except min-cut. But that's what the LR is. In fact, we also looked at k-nearest neighbors, random forests, neural networks, but logistic regression turned out to perform generally the best. So that's the one I'm showing here. Okay, so what's going on here? The bottom two rows here are kind of traditional classifiers. So it's logistic regression. Some data is missing, so we do imputation. That's the imp. And we might discretize things or not discretize. And so those are kind of standard methods that don't take any kind of strategizing into account. All the other ones are our methods that take strategizing into account. And so unsurprisingly, what you see is that if you look at the true columns, right, where we're evaluating it with everybody just reporting the truth, the traditional methods always do best. Right? The best entry is always in the traditional column, traditional rows. But on the other hand, if you look at the strategic evaluation, right, so we're looking at these incentive compatible classifiers. So the truthful and the strategic evaluation is always the same. But that's not true for the bottom two here. And so we see on the strategic columns, it's always one of our methods that actually does best. Let me briefly talk, kind of running out of time, but briefly I'll mention what these classifiers are. Incentive compatible logistic regression is just about getting the coefficients right so that you never have an incentive to drop a feature, that you would actually get a lower score from that feature being missing. And that's actually one that tends to do the best here. Min-cut is actually the min-cut algorithm that I just showed you before, except it's only on the empirical data. And so that doesn't really generalize very well because we only see a very small fraction of the examples. And so yeah, you see it performing quite poorly here. That's due to just it's not trying to generalize in any sophisticated way. It does a little bit better with discretization, but still. And then we also have this hill climbing algorithm that I think I'll skip over what exactly that is in the interest of time. That also does fairly well. Good. And here is more similar data now on a modified data set where we only left 4 of the features. And so now, but it's mostly the same picture. Again, now here you do see there's one case where traditional logistic regression with imputation actually is the best in a column. And now also the hill climbing method is sometimes the best. But generally the picture seems to be about the same, that the traditional methods tend to work best with truthfully submitted data, but our methods are better when there is in fact the strategic behavior that we're concerned about. All right, there's one more slide on what this hill climbing algorithm is. I'm going to skip over that. It's not that important, but you can find the details in the paper or ask me about it. Okay, I just want to wrap up with future research. As I said, I've in this talk not focused on these kind of settings where you actually really change who you are by taking an extra job and working off your debt. And there is some work on that, but I think there's a lot more that can be done there as well. Another question, this is one that we've been working on more recently, is that the experiments I just showed you required us to develop our own classifiers. But in many other contexts, like let's say we're thinking about computer vision or natural language processing types of applications, we might want to use something out of the box. And can we still do that while taking account of strategy? And just to give you a little bit of a hint of how we're trying to do that is if we go back to that picture that I used early on, where we kind of iteratively adapted the classifier in response to the agents changing their data and it eventually converging, that is the kind of approach that we're looking at there. And trying to figure out how well that actually works, both from theoretical and experimental perspectives. And related to that also is you could think about truly online models. So here, so far, I've assumed that we have some clean data that we can use as training data. And then once the system is deployed, then we're going to see the strategizing. In reality, you might have more of an online situation in the sense that, you know, the thing is already deployed. That's how we get some data. Then we change it. And so that changes how people report their data as well as the incentives have changed and so on. So you keep iterating that way. So that's again related to this kind of picture. So how should you think about those kind of online settings where things change over time and we really deploy the classifier, but also get the updated over time? All right, that's everything I had to say. So this was a pre-recording, but I think we have time for some Q&A, so I'll be there in person. And if we don't get to your question during the Q&A, again, please reach out to me, send me email, connect with me on social media, or find me at a future conference. Thank you very much.
Thank you very much. Thank you for the great talk. This is very exciting. So now we are open for questions, and we have a few questions lined up. Let's first start up from the first one. In mechanics of design, we often assume that the utility of known. However, consider the scenario of data marketplaces, the utility of data set may be determined later, such as the second uses of the data. Yeah.
Yes.
How can, yeah, go ahead.
Yeah. So that's good. So in mechanism design, that's a great question. If sometimes you don't know the value of the object you're buying yet, right? And this would be an example of that we might procure some data, but we don't know yet how valuable it is. One thing, of course, you could do is you could bid the expected value of the data or the object more generally. But another phenomenon, and that's one that actually would apply here, is that maybe you know something about the data that I don't, but that actually would be relevant for me, right? And I know something that maybe you don't. And these are what are called interdependent valuation settings, where my value in some sense depends on what you know. And that creates a lot of really interesting aspects, right? You get things like the winner's curse, that I might end up buying the data, but the only reason that I bought the data as opposed to somebody else is that I was unreasonably confident that it would be useful, but actually it turned out not to be useful. Another interesting aspect here is that data is non-rival, which means that just the fact that one person buys the data doesn't mean that nobody else can also buy the data or use the data. And so that leads to lots of interesting market design questions. They're a little bit different from the ones considered in this talk. But yes, very interesting questions.
Great, thank you. Another question is that you talk about a few NP-hard problems. Automatic mechanism design is very challenging. In the case of optimal design may not be feasible. How can we estimate or bound the optimality of the mechanism on the system or marketplaces so that it is still trustworthy to some degree?
Yeah, good question. So I think there are kind of two aspects in that question. One is finding the optimal mechanism. And the other one is trusting the mechanism that you did find, right? So the input to the automated mechanism design problem requires a distribution over the data, let's say over the types, right? And so that distribution may have just been estimated. and your estimation might be wrong. And part of the talk got into this a little bit, right? The generalization questions, so that there's this risk that, well, you really optimized the mechanism to this particular distribution that was based on your sample, but actually your sample didn't really reflect the true distribution. So how well does it generalize? And that in some sense is a separate question from the optimization question, right? So even if we know the distribution perfectly, the optimization problem can still be hard. Though it isn't always, right? So there are cases where you can actually solve for the optimal mechanism in polynomial time. We saw a few restricted cases here. Also, generally, if you allow for randomized mechanisms, you can solve for those exactly. Those turn out to be linear programs rather than integer programs. They might become very large linear programs, and there's some tricks to deal with those. But often we can actually find the optimal mechanism, sometimes also with the mixed integer program solver. You might ask questions about formal approximation guarantees, which you might get in some contexts as well, though often not. So yeah, there are those two aspects that are both important. So thank you for highlighting that.
Thank you. Given the time, probably the last question is that if we can we get some kind of interpretation or explanation of the mechanism design so that the communication between the design and the users can be facilitated?
Yeah, that's a great question. So many mechanisms in mechanism design are fairly easy to communicate, right? Like the second price auction, right? The highest bid wins and pays the value of the second highest bid. That's pretty easy to explain. One weakness of automated mechanism design type of methods is that sometimes the mechanism that they produce is very complicated, right? Really, you get a big table of lots of numbers, and it may not really be very transparent what those numbers are doing. In some contexts, that doesn't really matter, right? Because we're making our decisions and it's not necessarily useful that it's interpretable to users. But in other cases, it's very important that it's interpretable to users. And that's a tricky thing. We never really published anything about this, but we've thought a little bit about how you kind of force the optimization software to produce something that is a little bit more intuitive. You certainly could look at kind of a restricted class of mechanisms. And so we've done work on that. And my former advisor, Thomas Sandholm, has done work on that as well. And so that's one way to enforce interpretability, is just to look at a restricted class of mechanisms that are easy to interpret. But I think the more interesting question is, what if you don't necessarily at the outset have some type of mechanism in mind, but you want to make sure that whatever comes out has some easy interpretation, or at least it's not unnecessarily complicated? Those are really interesting questions, but I don't think we really have the answers to those yet.
Great. Given the time, we have to stop here. But thank you so much for your talk, and thank you for your support to the KDB conference.
Thank you. Thank you so much for inviting me.